A circus ride revolves 8 times in 5 seconds. What is its angular speed? 8 revolutions over 5 seconds. We know that 2 pi radians is 1 revolution, so we'll put 2 pi radians over 1 revolution. Revolutions will cancel out. 8 times 2 pi divided by 5, because that's the number of seconds there on the bottom. We're left with radians per second, which is the units for omega, our angular velocity. We get 10.05 radians per second. What is the tangential speed of the rider who's sitting 5 meters from the axis of rotation? When we have angular velocity, if we multiply by the radius, we get the tangential velocity, the tangential speed. So 10.05 radians per second times 5 meters should be 50.25 meters per second. A circus ride accelerates from 1 radian per second to 4.5 radian per second over a time of 12 seconds. So they're giving us some kinematic variables. Let's go ahead and record those. Omega naught is 1 radian per second. Omega would be 4.5 radian per second. And then t for time, lowercase t, would be 12 seconds. What's the angular acceleration during these 12 seconds? Here I'm going to use like WOTAT. That'd be angular velocity is equal to initial angular velocity plus acceleration times time. It kind of spells out a WOTAT. Easy to remember that way. We'd have 4.5 is equal to 1 plus alpha times 12. Subtract the 1 to the other side, you get 3.5 is equal to alpha times 12. So 3.5 divided by 12 will get us alpha angular acceleration. So 3.5 divided by 12 is what we're looking for. .29 radians per second square is our alpha. What is the ride's angular displacement? So it's asking for theta. Now we don't have to use our what we just calculated, but I'm going to because I know the formula better. I know that theta is equal to initial angular velocity times time plus 1/2 angular acceleration times time squared. There is another formula that just allows us to use the given. It's a little bit safer, but I'm confident in my answers. So I would have 1 times 12, or simply 12, plus 1/2 times 0.29 times 12 squared. So I take half of 0.29, multiply by 144, and then add 12 to it. Looks like I got 32.88 radians, the unit of theta. Draco says, moment of inertia is the rotational version of mass. The more mass you have, the more moment of inertia you have. Do you agree with this statement? Well, rotational inertia is mass times radius squared. So yeah, the more mass, the more rotational inertia. And rotational inertia is the rotational equivalent of mass. So yes, I agree. Rotational inertia is a sluggishness, rotational sluggishness. It doesn't want to change its angular velocity unless you apply a torque, just like we see linearly with masses. So it's rooted back down into Newton's first law of motion. 3 students are spinning in rolly chairs. All 3 students have the same moment of inertia, 500 kilograms meters square. Student 1 is spinning at 0.01 radians per second. Student 2 has an angular velocity of 3 radians per second. Student 3, 13 radians per second. Calculate the rotational kinetic energy of each student. Rotational kinetic energy, K-rot, is equal to 1/2 I omega squared. Each one of the students will have the 1/2. Each one of the students will have an I of 500. So 1/2 times 500, so let's say 250, times their angular velocity squared. So the first student would be 1/2 times 500 times 0.01 squared. Second student, 1/2 times 500 times 3 squared, or 9. Third student, 1/2 times 500 times 13 squared, or 169. I've written them all out first, and then we'll go back and just put them in our calculator to determine the values for these. First one is 0.025 joules. Second one looks like 2,250 joules. The last one looks like it's 42,250 joules. It's joules because it's energy. Will a ball released down an incline begin to roll if the incline has no friction? Explain your answer and provide a diagram to support your explanation. In order for it to roll, that would be an increase in the rotational velocity. To change your rotational velocity, that would be a rotational acceleration. The only way to get a rotational acceleration is to have an unbalanced external torque acting. If there's no friction, there's no source of this torque. If there's no torque, you ain't going to spin. So in order to rotate or change your rotational velocity, you need an unbalanced torque. And in this case, there is none. So it's not going to spin. It's just going to slide right down like it was a block. And then the part of the question says provide a diagram. I'm really not sure what I'm supposed to draw here. So if you want to draw a hill, draw a hill. I'm just going to cross that part of the question out. Angular momentum is equal to MVR is an equation that can tell you the angular momentum of a linear moving object in reference to a certain point. It's great information. Plank of wood is attached to a pivot point P, so we know P is the pivot. A baseball of mass is 0.5 kilograms, so let's go ahead and put the mass in the picture to make it easier. 0.5 kg is thrown at the wood with a velocity of 15 meters per second. So let's just say that velocity is equal to 15 meters per second so that it will strive. I think it's supposed to be strike, so let's fix that in the question. So it will strike the wood 5 meters above the pivot point. And then the question is going to ask us, what is the angular momentum of the system before it strikes the wood? Well, if the wood's not rotating, there's no I omega of the wood, because the omega is 0. Whatever the I is doesn't matter. If it's pivoting at the center, we know it's 1/12 ml squared, but 1/12 ml squared times 0 is still going to be 0. So the only angular momentum of the system is coming from the baseball, MVR, mass, velocity, radius. Mass 0.5, velocity 15, radius 5. Put that in our calculator, we get 37.5 kg m square over seconds is the angular momentum of our system.